Hi, my name is Javier Cisneros. I'm a PhD student in the group of professors Jaime Rodríguez and Carlos Jiménez at the University of A Coruña, Spain. This work is the result of a collaboration between our research group and Diego Rey and Dr. Miguel Balado from the research group of Professor Manuel Lemos at the University of Santiago de Compostela. I am pleased to present our recent work titled The Outer Membrane Protein FSTC of Aeromonas salmonicida acts as a receptor for Amonabactin siderophores and displays a wide ligand plasticity, structure-activity relationships of synthetic Amonabactin analogs. To develop strategies against pathogenic bacteria, our research group is focused in the bacterial iron uptake systems. Iron is an essential nutrient involved in a lot of metabolic processes, but has low bioavailability, because in aerobic media it's oxidized to iron 3 and precipitates as hydroxides. To overcome this difficulty, bacteria have developed sophisticated mechanisms, being siderophore synthesis the most widespread. Siderophores are high-affinity iron chelators produced and secreted by bacteria and internalized by specific membrane protein receptors. Our research group was the first to identify that Aeromonas salmonicida produces two catechol-type siderophores, Acinetobactin and Amonabactins. Amonabactins are a group of 4 related siderophores, which can differ in the presence of a phenylalanine or tryptophan, and in the presence or absence of a glycine. In previous works, we were able to identify FSTB as the membrane receptor of Acinetobactin, but the receptor or receptors for Amonabactins remains yet to be discovered. So, the main objectives for this work were to identify the Amonabactin receptor in Aeromonas salmonicida and deduce the structure-activity relationships for this receptor. Genetic analysis of the Amonabactin cluster allowed us to propose FSTC as the membrane receptor for Amonabactins. In order to prove it, we constructed 2 mutants. The first mutant, called ABL1, by deletion of the ENV gene, is unable to produce any siderophore, and the second one, a double mutant which additionally is unable to synthesize the FSTC receptor. Due to its inability to produce siderophores, both strains are unable to grow in an iron-deficient media, but when we added a mixture of Amonabactins, only the strain with the FSTC receptor was able to grow. These results greatly indicate that FSTC was involved in the acquisition of Amonabactins. However, because the structural diversity of this type of siderophores, it's necessary to test individually the ability of each one of the 4 Amonabactins to be internalized through the protein receptor FSTC. So, we decided to synthesize the 4 natural Amonabactins. Although the synthesis of Amonabactins has been previously reported, we designed a new synthetic route in order to optimize their synthesis. The 2 novelties introduced are the use of isopropyl as catechol protecting group and the formation of all amide bonds by activation of the carboxylic acid with N-hydroxysaxonamide. This strategy allowed us to improve global yields. Once the 4 Amonabactins were synthesized, we evaluated the ability of each form to promote the growth of the 2 mutants under iron restriction conditions. While the strain without the FSTC receptor was not able to grow in any range of concentration of Amonabactin added, the strain with the receptor intact is able to grow in all ranges of concentrations tested, as we can see in the figure. These results prove that FSTC mediates the uptake of all Amonabactin forms. In addition, this bioassay also showed that long Amonabactins, those that have glycine, displays higher siderophore activity than shorter ones. Finally, in order to reduce some structure-activity relationships for the FSTC receptor, we synthesized 4 simplified analogs, 2 monocatechol and 2 biscatechol, with different linker lengths, using similar synthetic pathways that were used for the natural ones. The monocatecholate analogs 5 and 6 did not display any siderophore activity. However, the biscatecolate analogs 7 and 8 were able to promote Aeromonas salmonecidea growth. These results show that biscatechol structure is necessary for recognition, and in the same way as natural amonobactins, 15 atoms length linker between the 2 catecholamide units maximizes siderophore activity. We have proved that FSTC is the transporter of the 4 different forms of amonobactin in Aeromonas salmonecidea, showing that it is a versatile siderophore receptor capable of internalizing rather different siderophore structures. Biscatecholamide structures with 15 atoms length linker displays maximum biological activity, which corresponds to that found in the natural longer amonobactins. Analogs synthesized in this work could be good candidates to develop fluorescent probes or the Trojan horse strategy against pathogens of the genus Aeromonas. Our work was supported by the Spanish Ministry of Science and Xunta de Galicia grants. Thanks for being interested in this work.